Okay, so again, we want, starting my timer back up, our goal here was to explore simplifications of the first law. And again, point out the fact that it's not uncommon. I think if you went to Wikipedia, you probably, Wikipedia, the first law of thermodynamics, you'll probably find Q minus W is equal to U. That's okay as long as you understand we're saying heat in is positive, heat out is negative. Right? Heat in is positive, heat out is negative. Work out is positive, work in is negative. If you want to use that sign convention, that's fine. This is how I will try to work problems, probably throughout the course, because I find it's easier, I really truly find it's easier to think about the first law as in minus out equals change. And if you think about it that way, you end up with less to memorize, or you end up kind of grouping together like terms and thinking about like terms easier. The brain tends to grab onto them a lot easier than trying to memorize an abstract equation with lots of terms. It's a little easier to think about it in minus n equals change. We can have heat or work in or out, and if it's stationary, the only type of energy that changes is the internal energy. All right, so in chapter 2, we introduced a few things about some different kinds of work that you might encounter throughout a thermo course. We talked a little bit about how heat transfer can occur. Our first law is typically our best tool for trying to find the heat transfer. And unlike chapter 2, we can no longer just simply assume that the heat is negligible just because they didn't tell us anything about it. We're actually going to have to now, typically, unless they tell us the heat is zero or negligible, we're probably going to have to solve for the heat or assume it's a value we can find. Okay? And again, the first law is typically our best tool to find it. Now, piece of information, this text, the Changle and Bowles text that we're using, they will use this adjective, a weighted piston cylinder, to refer to a device where the volume can change but the pressure will remain constant. So when you see this adjective weighted, they're telling you you can assume the pressure is constant. They're telling you that a constant force or constant weight has been added to that piston, to the lid of that piston, and so it's going to apply a constant force to that lid spread out across the area of that piston face, and that causes a constant pressure to be applied to the contents within, which is our system. So, if they do not tell you, at least in our text, I've seen some texts where just any time you have a piston, you're supposed to assume it's constant pressure. That is not the case. Okay, a piston cylinder is a generic closed system where the volume can change. Okay, remember this is total volume. V with a cross on is volume. So generic closed system where volume can change. That's a piston cylinder. A weighted piston cylinder, that is a piston with constant pressure. Piston cylinder, not necessarily constant pressure. They need to tell you it's constant pressure, and one way they'll do that, in the problem statement, they'll just say assume the pressure is constant or during a constant pressure process, or they'll use this adjective, a weighted piston cylinder. They're telling you you apply the constant weight, that causes a constant pressure to be applied to the system. Okay? Now, why that's important? Well, we'll see that throughout the course from this point forward. But the reason that's important is because in Chapter 4, we're going to focus on moving boundary work. And I think I introduced this briefly in Chapter 2, but this is really going to be our focus of Chapter 4. One of the types of work we can encounter is moving boundary work. Okay? So the idea is if I've got a piston cylinder, right, which we'll often just draw kind of the cross section, right? We'll draw, the idea is that I've got kind of this lid that can move. This lid can be pushed up and down within the cylinder that's contained within. Okay? So that means I can change the volume in here. If I've got a gas, I can compress that gas, or I can pull it out and I can expand the gas, right? So I can, by adding or removing energy from this, I can cause this to expand or contract. Anytime if the volume of a system changes, then we must compute the work done by the system to cause the volume change, or the work done to the system to cause the volume change. Either one or the other. Now, what is work? Well, again, remember, work is the integral. So let's talk about boundary work. Again, work being the integral of force with respect to distance. Well, what causes, if I've got a system that's being compressed or expanded, right, if this thing expands into the surroundings, what causes that expansion? What is the force driving that? Well, that is the pressure. The pressure, and the pressure is not a force by itself, right? Pressure times area gives me a force. Because again, pressure is equal to force per unit area. And the pressure is what causes the force. So to get a force here, I need to take pressure times area. Integrate this quantity with respect to distance. The distance traveled, right? This is my ds. The distance that this lid travels up and down. Okay? Now, just conceptually, I want you to think about something. What happens if I take an area and I multiply it by a third dimension? What do I get? Right? Area times a third dimension. Well, that's a volume, right? An area times a third dimension. If I take the volume of a box, length times width times height. If I take length times width, that gives me the area of one face. Multiply by the height, the third dimension, that gives me the volume. Same thing here. If I take this area and I multiply by a tiny, remember this ds represents a differential tiny distance. If I take an area times a differential tiny distance, I get a differential tiny volume. And so what we find, the boundary work, we'll compute it, if we compute it in the out direction, the work that the system puts out into the surroundings to expand is from the initial volume to the final volume, pressure with respect to volume. Okay. And so graphically, that kind of looks like this. Right? So if I go from one volume to another, if I expand, right, the area bound by this curve to get from this pressure-volume combination to this pressure-volume combination, the area bound by that curve, the integral, the pressure with respect to volume, represents the work done to achieve that. Notice that if I've got a different path, something up here, this is a different area. And remember, work is path dependent, just like heat is path dependent. The integral, the area, is going to be dependent on whether I have a path down here, which you can't see that because that's a different color. Right? I can have a path down there, I can have a path straight across, I have a path up here, and I get different works. Because how pressure is a function of volume determines that work quantity. So I will need pressure in terms of volume. How pressure, I need pressure as a function of volume. How does pressure vary as volume varies? Well, there's a few ways it can occur. The simplest one is it could be constant. I could have constant pressure. Right? Again, if I'm integrating pressure with respect to volume, if the pressure is constant, then that's easy to integrate. Right? Then it's just pressure times delta V. If it's an ideal gas, if it's isothermal, then that's actually pretty simple. Another common one we get is what we call polytropic or polytropic. That is where P times V to some unknown power n or some measurable power n is equal to a constant. And we'll see that a little bit later, probably not today, but probably in the next lecture. But a polytropic process, which is kind of more of a realistic scenario that we would normally, if we actually had a piston cylinder with some gas in front of us, that's probably how it would behave, as some form of polytropic expansion or compression, and I would need to do some experiments to measure N and C. Now, we don't have a cylinder in front of you that you can measure. I just realized I've got this glare here. I apologize. We don't have this cylinder in front of us that we can measure the glare or measure the N and C values for. So we'll have to, those will have to be given to you, or you'll have to be able to solve for them algebraically. Okay? All right, so these are kind of the main problems you'll see. It's either constant pressure, polytropic. Another one we'll see is in here. Could also be linear, which occurs a lot of times with a spring. So if the piston has a spring attached to it, that spring provides a linearly varying force as the system expands or compresses. That's where P is equal to some constant, a slope if you will, times volume plus some other constant. We like A and B, but if you could use M and B. Again, I would need to know pressure as a function of volume to plug in here and actually do this integral. If you're allergic to integrals, you're probably in the wrong place. You should have already learned that. I don't know what to tell you. I'm expecting you to have integrals and calculus before you get here. So if you can't do integrals, you might want to get that looked up. I am going to expect you to be able to do integrals. Somebody complained about that on a student evaluation. So anyway. Example, which is probably not a bad place to stop. So yeah, let's stop there. We'll pick up on the next video. We'll work the example.